Hi everyone, I'll give a short introduction to the paper Long-Tail Classification with Multi-Granularity Semantics by Liu Yang and Wang in this video. Let me start with the problem setting. In long-tail classification, the class distribution is highly uneven. A few head classes contain many training samples, while many tail classes contains only a few. The result is that the standard training is dominated by the head classes. So even if the model achieves decent overall accuracy, the learned space feature space is so much stable for common classes than for the rare ones. I think the key intuition here is that it is not only about the counting of examples, it is also about the representation quality. Tail classes simply do not provide enough evidence for the model to learn robust class structure on their own. So the real goal is not to boost real classes artificially, but to improve tail recognition without sacrificing the head class performance. Many existing long-tail methods try to fix this using reweighting, resampling, or augmentation. These can help, but they do not answer a more selective question, the question that which classes should transfer useful knowledge to which tail classes. That matters because transfer is only useful if the source class is meaningfully related to the target class. The paper gives the simple intuition that transferring from dog to airplane is unlikely to help much. This is where semantics enter the story. The authors argue that class can share useful properties even when they are not neighbors in the label hierarchy. For example, turtle and snail may belong to different branches, but they share traits like being slow moving and shell breeding. So the paper's critique is that balancing alone is too blunt. It adjusts attention, but it does not reason about semantic relatedness. The next step is the paper's core semantic idea. A plain class name contains only limited information, so the authors use a large language model to generate standardized descriptions for each class. Importantly, the LLM is not used as the classifier. It acts more like a semantic teacher that helps each label expand into richer attributes, such as appearance, behavior, or functional characteristics. These descriptions are then embedded using a sentence transformer, and pairwise similarities are computed to form something called semantic similarity matrix, and from that into a multi-granularity semantic graph. The phrase multi-granularity, it matters a lot here. Some relations are coarse, some are fine-grained, and some appear across different hierarchy branches, right? So the paper explicitly argues that the cross subtree relations are exactly what fixed label hierarchies miss. A nice example from the paper is that the airplane can become semantically close to a bird because both share the concept of flight, even though the label hierarchy would not capture that relationship well. Now, once we get the semantic graph, the method injects that knowledge into the representation learning. This is the SKCL part, also called semantic knowledge-driven contrastive learning. At this high level, the model keeps only the top k most similar classes for each class, which is important because too much prior knowledge generally introduces noisy or misleading behavior. The framework has two components, a standard classification branch and a semantic contrastive branch. In the contrastive branch, a sample is encouraged not only to align with its own class prototype, but also with the prototypes of semantically related classes. A prototype here is basically a representative class center in the feature space. So geometric intuition is pull a tail samples towards its own class, but also towards the few neighboring classes that are semantically meaningful instead of treating all other classes equally. So for me, this paper's main conceptual contribution is that the semantic structure becomes transferable knowledge. This also explains why the method helps the tail classes. Tail classes usually do not have enough visual evidence to organize themselves reliably in the feature space, so semantic neighbors provide the structure support. The paper describes this as enabling both horizontal and vertical knowledge transfer across the class space. In other words, transfer can happen within the same level and also across different semantic granularities. Empirically, this shows up most clearly on the C500 LT, with imbalance factor of 100 compared with BCL and concat mix. SKCL generally improves the few shot group the most, while also slightly improving the mini shot group and the overall accuracy. So the improvement is not just that the tail classes get more emphasis, it is that they get better guidance. So my proposed extension is to ask whether this graph should remain static or whether it should adapt as class prototypes evolving during the training. The hypothesis would be that the dynamic graph could improve tail transfer when the initial text-based semantics are incomplete, but the risk is that the semantic drift if the graph becomes unstable. I think it is a good extension because it stays very close to the core of the idea, but now we also test whether semantic structure should be fixed or adapted. So my final takeaway would be rare classes do not need more samples, they need better semantic neighbors, and SKCL help us in doing that.